There's this incredible technique that can solve a whole class of really tricky tree problems. I'm talking everything from finding the longest path to picking the best set of nodes, all in linear time. It's elegant, it's powerful, and today, we're going to unlock the superpower, dynamic programming on trees.
So to kick things off, let's start with a classic puzzle. Imagine this tree is a network of computers. Your job is to pick the maximum number of computers you can to run some task. But here's the catch. You can't pick any two computers that are directly connected. Think about it. Any choice you make over here immediately affects your options over there. So how do you find the absolute best combination?
Well, the solution to this puzzle, and a ton of others just like it, is dynamic programming on trees. It's a really systematic and powerful way to handle these kinds of problems, where your local choices have these big, cascading consequences across the whole structure.
Okay, so how does it actually work? The magic of TreeDP really comes down to one single core insight. You build the solution from the bottom up.
Here's the secret sauce. We figure out the answer for any given node by using the answers we've already calculated for its children. And this only works because trees have a special property. They don't have any loops or cycles. That structure is a guarantee that we can solve the problem for all the kids before we ever have to worry about the parent. We're literally building our way up from the leaves right to the root.
So in practice, how do we do this? We use what's called a post-order traversal. All that means is we visit a node after we've already visited all of its children. It's kind of like a family tree, right? You can't get the full picture on the parents until you have all the info from their kids. It's the exact same idea. By the time we work our way all the way up to the main root, we've combined all the wisdom from below, and bam, there's our final answer.
Now, this bottom-up approach is super versatile, but most of the TreeDP problems you're going to run into fall into one of three core patterns. Let's start building our toolkit.
First, you've got your basic subtree DP, which is really just about collecting info up the tree, like counting nodes. Then there's the two-state pattern, which, by the way, is exactly what we need for our computer network problem. And finally, there's the really powerful rerouting pattern, which you use when you need the answer from the perspective of every single node.
Let's dive into that include/exclude pattern. It is perfect for our maximum independent set problem. Here's the strategy. For every single node in the tree, we're going to compute two different values. What's the best outcome if we include this node in our final set, and what's the best outcome if we exclude it?
So here's how that logic breaks down for any node. Let's just call it U. If we decide to include U, the rule is simple. We absolutely cannot include any of its direct children. But if we exclude node U, then we're free. For each of its children, we can just take whatever their best result is. It doesn't matter if they chose to include or exclude themselves.
So how do we turn that logic into formulas? Well, to get the include U value, you take 1 for U itself, and you add up the exclude values from all of its children. It has to be the exclude values because if we take U, we can't take its kids. Now for the exclude U value, we don't get the point for U itself, but we get the best of both worlds from each child, which is just the maximum of its own include and exclude states. We just do this for every node, starting at the leaves and working our way up.
All right, on to our second pattern, rerouting. This one is really cool. What happens when the problem asks for an answer for every single node, as if each one were the root of the whole tree? A great example is finding the sum of distances from one node to all others. Trying to just brute force it and run a full DFS from all n nodes would be way too slow, probably O(n) squared. Rerouting is the clever technique that gets it all done in O(n).
The method is this beautiful two-pass process. First, we do a post-order pass, just like before. We pick any old node to be our temporary root, let's say node 0, and we calculate initial info like subtree sizes from the bottom up. Then, once we have the answer for our temporary root, we do a pre-order pass. This means we go top-down, from parent to child. And in the second pass, we use a clever update formula to quickly calculate a child's answer using the answer we already have for its parent. It's a brilliant way to shift perspective without redoing all the work.
And now for the best part. The reason we call this a superpower, the incredible efficiency. Let's break down why these algorithms are so darn fast.
The math here is actually surprisingly simple. A tree with n nodes always has exactly n-1 edges. Our DP algorithms are built on a depth-first search, a DFS. And in any DFS on a tree, you travel down each edge once, and then you travel back up that same edge once. That's it. The total number of operations is directly proportional to the number of nodes. This gives us a linear time complexity, O of n. All that means is if you double the size of the tree, you basically just double the work. It's incredibly scalable.
As you can see here, both of our big patterns, subtree DP and rerouting, hit that O of n time complexity sweet spot. The space needed to store our answers is also linear. The one little detail to keep in mind, though, is the recursion call stack. It can get as deep as the height of the tree. So if you get a really long skewed tree, that stack depth could also technically be O of n.
So you've got the theory. Now let's get practical. Here's some advice to make sure you can actually use this stuff correctly when it really counts.
All right, here are the common traps you really want to avoid. First, and this is the bug I see most often, you forget to tell your traversal not to immediately go back up to the parent it just came from. That sends you into an infinite loop. Second, don't assume trees are always nicely balanced. You can get a skewed tree that looks more like a linked list, which can make your recursion depth huge. And finally, always check your input. Make sure it's actually a tree before you run a tree algorithm on it.
Okay, if this topic comes up in an interview, here's your game plan. Start by clearly defining your DP states. Say my states will be include you and exclude you. Then write down the recurrence that connects them. Be ready to explain why it's O of n by talking about how you traverse each edge twice. And hey, if you're doing a rerouting problem, knowing that core update formula is a huge win. It shows you really understand the mechanics of efficiently shifting the answer from parent to child.
Of course, the best way to get good at this is to actually practice. For the include/exclude pattern, the classic problem is House Robber 3 on LeetCode. And for rerouting, you can test your skills on sum of distances in tree. I'll put links below. Seriously, give them a try.
So if you only remember one thing from all of this, let it be this. The whole philosophy is just about delegation. You let the children figure out their own subproblems first, and then the parent's job becomes easy. You just combine the results.
And this brings us to a final, really important point. This whole bottom-up, children-first logic works so beautifully because trees don't have cycles. But what happens when you introduce a cycle? When you have a graph with loops, who's the child and who's the parent? The whole idea gets messy, right? And that question is really the gateway to the next level, the much more complex but fascinating world of DP on general graphs.